This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning. Just a small announcement. I think you may have seen the email I sent you. There won't be any consultations this afternoon. I'm still not feeling well, so we'll try to make up for it. So we will do the lectures. I hope to be able to do that this week. In any case, we will organize things for lectures. Lectures will be on. So bear with me, because I'm sort of not feeling great. Last week, Guizhou talked about steady-state errors, and he introduced sensitivity transfer functions. So sensitivity transfer functions are very useful beyond steady-state errors. But steady-state errors was one outcome. You could see that you can easily write some formulas, useful formulas, for calculating steady-state errors via the sensitivity transfer functions. Now, in today's lecture, I want to go further and talk about transient response. And actually, we want to talk about how to translate some design specifications. And design specifications can be on rise time, settling time, or overshoot. And we can translate these specifications on step response to locations of closed-loop poles. So basically, if I tell you you need to achieve such and such overshoot, such and such rise time, settling time, you can translate that into desired locations of the closed-loop poles. So by the way, steady-state errors and all of these things we will talk about in today's lecture constitute typical design specifications in design problems. So you can pose design specifications in time domain, and that's what we're talking about here. But later on, we will also talk about specifying these design specifications in frequency domain. So we will talk about how to do both, right? So typically, you will be told by your boss, I want you to achieve maybe zero steady-state error, overshoot not more than 10%, rise time maybe 1 second or less than 1 second, settling time less than 5 seconds, etc. And you need to design a system that achieves these specifications. So today's lecture covers this step of translating design specifications into locations of the closed-loop poles. Later on, we will learn how to design controllers to move poles in the desired region. But today we're just talking about how to translate design specs into locations of poles. And then an important part of this lecture is also to talk about fundamental limitations to performance. You will see that what can happen is given a system, given your plant, you might have a situation where I can give you a set of design specifications that is unachievable with any controller. I mean, and this is sort of intuitively clear. If you ask me to win in the Olympics, 100 meters, or to win like heavyweight boxing championship, with guys like Mike Tyson, I can't do it, right? So some things are unachievable for me, right? So every system you consider might have similar fundamental limitations to what it can achieve. So we will present two such results. By the way, there are books written exclusively on this aspect. Just books dedicated to analyzing what are the fundamental limits to what you can achieve. But in our lecture, we will just consider two cases, how, for instance, unstable zero affects, overshoots or undershoots, etc., right? So we will talk about just specific situations which are commonly encountered, right? But you need to be why is this important? Well, your boss comes and tells you, you need to achieve these design specs. And then, you go and say, well, actually, you analyze your model, you realize that it's unachievable So you go back and you say, it's impossible. What you're asking is impossible. If he wants to sack you for not achieving what he asked you, right, you say, well, it's impossible. What you're asking me is impossible. So it's always useful to understand what's possible before you start designing things, right? Okay, so that's the scope of the lecture. So we will first motivate things a bit. I already did that partially. And we will look at design specifications first for second-order systems. You will see that I will present like exact formulas for second-order systems only, but these formulas are used as a rule of thumb for higher-order systems. So for higher-order systems, these formulas are not exact, but they are used as a rule of thumb in your design. So we will talk about that, and this will lead to a natural definition of so-called dominant poles in your system. And then in the last part of the lecture, we will talk about two results on fundamental limits and conclusions. So that's what we want to do. All right. So why are we doing this? Well, typically, if you're designing your system, stability is not enough. Stability is typically necessary. You have to achieve stability, but it's often not enough. And then you need to specify typically further conditions on what acceptable transients are. For instance, if you are designing control loop for room temperature control in this room, and you say, okay, my settling time is 5 years. Yeah, I will get to 20 degrees in 5 years, right? So you change from 0 to 25 desired temperature, and it takes 5 years to go from like 0 to 25. That's not acceptable. Similarly, if you have overshoot that's going to 100 degrees and then settles at 20, that's also not acceptable. So in every system, depending on the application, you can define meaningful desired specifications. What is a good system in that specific case will depend on the application, right? And what you want to achieve, right? So we will provide rules of thumb for pole locations to achieve such design specifications. So we want to translate how overshoot, rise time, settling time can be encoded in complex domain in terms of locations of poles. And obviously, we also need to know about these fundamental limits. So we will present two results. So you will see through examples and actually specific results how you may not be able to achieve some things in certain systems. So let's consider now second-order systems only. So by the way, the transfer function at this stage is given by this. So I'm not only considering second-order systems, but a specific class of second-order systems, right? So note that here g at 0 is 1, right? So why is g at 0 important? What do you think? Last lecture you talked about steady state errors. So how do we find steady state errors? We typically look at, if the system is stable, use final value theorem. So S tending to 0 is important. So G evaluated at 0 is important for steady state errors. All right. So in this case, we assume that G at 0 is omega n squared divided by omega n squared. That's 1. Right. So that's a very special class of systems. Now, I remind you that if you find the poles of this specific transfer function, by the way, there are no zeros. There are only poles, right? So if you find poles of this transfer function, a real part of poles is given by this formula, where zeta is the damping and omega n is the natural frequency, and the damped frequency or imaginary part of the poles is given by this omega d. And omega n is the undamped frequency. By the way, omega n is like the distance of the poles from the origin. That's like polar coordinates, coordinate. And zeta is related to the angle, right? So zeta and omega n are related to polar coordinates, and sigma and omega d are Euler coordinates for the poles of this transfer function. So what we want to do now, and I will not present proofs of these things. There are books like Ogata and Franklin and Powell that take a few pages in the book to derive these formulas. Although we are dealing with a second-order system, deriving some of these formulas is non-trivial. I will just give you the formulas and explain how you use them in design. Okay? But if you are interested in proofs, you can look up Franklin and Powell, for instance. So I remind you that the step response typically would look something like this for a stable system. And in this case, I actually plotted step response slightly more general than the step response for this guy. So step response for this guy, for instance, will never exhibit undershoot. But for this lecture later on, when we talk about fundamental limits, it's useful to remind ourselves what undershoot is. So steady state value is basically where your signal would converge as time goes to infinity. And then you can talk about undershoot. That's the, and typically you can talk about percentage undershoot, overshoot. So it's the amount, of sort of, we can say like minimum value, right, of the output before it goes to the direction we want. Overshoot is measured just above the y infinity, right? Rise time typically is defined as time needed for response to go from 10% of y infinity to 90% of y infinity. And settling time is typically related to this delta. You tell me what delta you want. Typically delta is chosen 1% of y infinity or 5% of y infinity. And then TS is basically the time needed for the response to come within delta neighborhood of y infinity and stay there forever. Right, so that's the settling time. By the way, each of these things, these features are different features. So you may have all sorts of different situations. For instance, you might have that some system has, if you're comparing two systems, rise time in first system can be smaller than in the second system, but settling time can be larger. So it may take longer time to settle, right? So all of these are independent. And in order to specify your desired response, you typically need to tell me a bit about every one of these. Another one that I'm not mentioning here is steady state errors, which you covered in the last lecture. But that's also typically part of the design specifications. I might tell you, I want 0 steady state error, and on top of that, all of these things, right? We will learn how to deal with the steady state errors differently. In this lecture, let's just talk about these things. So what I want to now go is what I want to do. I want to concentrate on overshoot rise time and settling time, and I want to relate them for this transfer function in terms of constraints on sigma, omega d, omega n, zeta, etc. So I want to say, if you want to have overshoot for this transfer function, step response for this transfer function, if you want to have overshoot less than 10%, then zeta has to be such and such. If I want to have rise time smaller than so many seconds, then omega n has to be such and such. If I want to have settling time smaller than something, then sigma has to be satisfy certain constraints. So I want to translate constraints on these guys, overshoot rise time and settling time, into constraints on locations of poles of this transfer function. In other words, sigma, zeta, omega n, omega d, right? So I want to relate them, basically. Now, proofs of these things, as I said, are given in books. I will just use it off the shelf, but do read through these proofs just to get a sense of where these equations come from, right? So let's go one by one. So settling time. So what's settling time? So settling time, it's the time it takes for a response to get to within delta neighborhood of y infinity. So typically delta is given as, let's say, 1% of y infinity or 5% of y infinity. There are also some books that give you 2% formulas, etc. So the formulas that I will present here work with 1% delta. So delta is 1% of y infinity. So settling time defined in this way By the way, if I define this to be 5%, then would settling time be larger or smaller? Smaller, because you will get to within 5% earlier, and you will stay there forever, right? But with 1%, then this is the sort of condition. If you tell me what settling time you want, so this is, your boss comes and tells you, I want settling time to be 1 second, then you would know that for this transfer function, you would need to satisfy that sigma has to satisfy this inequality, where sigma is basically the distance of this vertical line, from the imaginary axis. So basically, sigma is the distance. Always this sort of line is in the left half plane. We are stable, but we have to be more stable. Like we have to be away from the imaginary axis to satisfy something like this. So for instance, when settling time is 1 second, sigma has to be at least 4.6 far from the imaginary axis. So you have to avoid this brown region. So if you remember, the stability region is the left half plane. So we have to avoid right half plane anyway, just to have stability. But if you want to achieve settling time smaller than some number, then you have to actually be more stable, if you want, right? All the real parts of your poles have to be outside this shaded region. So they have to be somewhere here, right? So, well, you can ask yourself, well, where did this 4.6 come from? Well, it comes from first finding what the response is in time domain, using this definition, this is the delta that we are using, and then calculating really, well, how settling time is related to the real parts of the eigenvalues of that transfer function. And you can do that, right? All right, so how about rise time? So rise time that we are using, definition is basically the time it takes for a response to go from 10% to 90% of y infinity. So rise time somehow captures the speed of your system, the speed of response. If rise time is very small, the system would quickly react. If rise time is large, then the system is sluggish. It takes forever to react, right? So if you want to, if you give me now a rise time that you want to achieve, you can again show, and Franklin does that omega n, which is the undamped natural frequency of the poles, should be satisfying this inequality. What does that mean graphically? Well, you definitely mustn't be in the right half plane. Right half plane is always shaded. But this now tells you that you also have to avoid this semicircle in the left half plane, because omega n is really like the distance of your poles from the origin. Right, so you are basically avoiding this semicircle. Again, where does this 1.8 come from? From the analysis of the step response and the constraint that you are given. Similarly, if you want to have a constraint on overshoot, that can be related to damping. Now, this relationship is not possible to write, well, it is possible to write explicitly, but it's messy. So it's easier to write it down as a diagram. So what does this give you? So it gives you the relationship between percentage overshoot on this side and the damping on that side. Again, this is only computed for transfer function like this. So we apply step input to this transfer function, we observe the output, and these are the conditions you need to achieve on the damping factor in order to get certain overshoot. So, by the way, if you, for instance, say, I don't want to overshoot more than 5%, so you basically say 5% overshoot, well, then damping should be 0.7, right? So you are, in a way, well, you're avoiding this sort of region. So this angle here is related to your damping. It's arc sine of the damping factor. And you have to avoid this region as well. So if your poles are in this white region, right, then for that transfer function, you will achieve the desired overshoot. By the way, the smaller the damping, the smaller this angle is. Because when sine is small, then the angle is small, right? Sine close to 0, angle close to 0. So basically, zeta close to 0 means that this angle is very small, and that you may allow poles very close to the imaginary axis, right? So I mean, they can be close, in this sense, but they have to be always sort of within this triangle to maintain the damping factor. Note, as damping is reduced, right, as this angle becomes smaller, then you may exhibit, 90% overshoot or 100% overshoot. So that means that you will reach y infinity, 2 times y infinity before you start converging to y infinity. So you have big oscillation, right? So that's obviously, undesirable. Now, what is desirable in which situation? That depends on the example you consider. For instance, there are applications where you want to have 0 overshoot. You don't want any overshoot. And there's research, that sort of research papers that publish controllers that achieve 0 overshoot. Why would this be important? Suppose that this output here is basically position of an element. So I sometimes have capstone projects working on maglev train. We have a lab equipment that's magnetic levitation. So you apply current, to some electromagnets, and it can lift a table, which sort of emulates what the train does, right? So if you apply too much current, then you would push this thing too far, and you will hit physical boundaries, and you might damage things. So you would hit things with like physical limits with certain force. So you may want to have 0 overshoot. You don't want hitting this with a huge force, right? There are lots of other examples where overshoot is just not desirable. In this particular example, you always would get overshoot when you have complex conjugate poles, right? And this is the functional relationship. This is an open book exam. You can always use this, from books. If you are asked to do something like this, you will be given, well, you can bring this diagram to the exam. So what does this mean altogether? Well, if I give you constraints on overshoot, rise time, settling time, you can come up with a region in complex plane that you need to avoid in order to satisfy all these 3 requirements. Now, this is only true for second-order transfer functions that I presented earlier, but we sometimes use this as a rule of thumb when designing higher-order systems, right? But it is correct and true for that transfer function that I presented to you earlier. So basically, brown color represents the forbidden region. So you see, it is sort of intuitive because I was telling you before, stability is always necessary, but often it's not sufficient. So in order to satisfy design specifications, like what we listed here, overshoot, rise time, settling time, you have to constrict more the region in which you want to place your poles of the transfer function. So we will learn how to move the poles of the transfer function by designing controllers later. This is just translating the specs. This is sort of telling you what you need to achieve, right, in complex domain. So, as I said, a second-order systems case is, basically you have exact formulas, but for higher-order systems we will use these formulas as rules of thumb. And in particular, these formulas can give you good results if you do the following. You use so-called dominant poles. And if you have 2 dominant poles, what are dominant poles? They are the closest ones to the imaginary axis. They are the dominant poles. So you may have 100 poles, but 2 poles would be perhaps closest to the imaginary axis. And if these 2 poles satisfy all the requirements we presented, and all other poles are far away from the imaginary axis, then the rule of thumb that you use will give you good results. So we will later on see how to do design in frequency domain. It's much more powerful than this design, but why I like and present this sort of design specs first, because it's easier to understand, I think. I think this is much easier to understand than when we go to frequency domain, right? All right, so what are the dominant poles? Well, suppose that you translated your overshoot, settling time and rise time into a region like this, then if your system is fifth order, what you can do is you can place two poles, close to imaginary axis, and all other poles you move far away. Then those rules of thumb would give you good results, right? So, and this is often a design technique that you would follow, right? It's not universal, but it's sometimes, possible to use it, okay? All right, are there any questions? Because I will now move to something that looks very different. Any questions? All right, thank you. So let's now move to fundamental limits. So as I said, sometimes you cannot achieve certain specifications. So I can give you sometimes specs that are unachievable with any linear controller. Interestingly, there are situations, and this is what I did in my research, there are situations where you can show that no linear controller exists that will achieve those specifications, but a non-linear controller exists that does achieve specifications. So by generalizing the class of controllers, sometimes you can sort of beat these fundamental limits. Fundamental limits are really for linear control sometimes only. So this is not always true, and it is still an open research area, right? So there are still papers that are being published on this research topic. So in any case, it is very important to understand what's fundamentally unachievable before you start design. So what are the red lights, red flags? If you have an unstable pole, that's a red flag. If open loop plant has an unstable pole, so basically if you're trying to stabilize upper equilibrium of this guy with some torque, right? This is unstable in open loop. If I just let it, evolve by itself, it just goes away. So it's unstable. This guy is stable, right? If we linearize system around this equilibrium, we'll get stable system. Linearize about this equilibrium, we get unstable system. Unstable pole spells trouble often in terms of what's achievable. Another thing which is really perhaps surprising, and we never talked about zeros, but it turns out that unstable zeros can cause a lot of problems. Actually, zeros in general would constrain what you can do. And we'll present some examples and then some results that summarize the effects of zeros in some specific situation. But that would really tell you, so often people ask me, well, I don't have to care about zeros then. Well, you do when you design, because the zeros might pose, unstable zeros in particular, might pose fundamental limits to what you can achieve in terms of design. So if you remember, unstable zeros and undershoot, when I was talking about it, I was telling you, well, I was giving you an example of motorcycle. So when there are races and they want to turn right, they go far to the left. And the faster they go, the further to the left they need to go in order to turn right. That's basically an example of undershoot. Now, what I also mentioned, you may remember, is that these transfer function systems that have such systems that exhibit this sort of thing often have unstable zeros. So unstable zeros in the plant model would force you to have some undershoot. We will now look at this in an example. So look, what I'm giving you here now is a transfer function, and let's look at this transfer function. So this transfer function has a stable pole at -1, and pole at -2. So the dominant pole is -1. The closest one to the imaginary axis, it's -1. And then what we are looking here is a family of transfer functions that are parameterized with this constant c. And note that c can be either positive or negative, and c is really the zero of the system. So if you now plot step responses of this system for various values of c, you find that response for C equals 0.1 is basically this. C 0.25 is this, etc. So, and then negative C's are plotted up there. So what can we now just observe in this example? Well, if C is small, then, so note, larger C, positive C, basically responses move in this direction. When C is smaller, responses move in that direction. And what is this? Well, this is the amount of undershoot. So the smaller, the closer the zero is to the imaginary axis, and it's unstable, because C positive means that the zero is unstable. Zero is in the right half plane, right? So, and the closer the zero is to the imaginary axis, the more undershoot you will exhibit in the step response. Now, and then you may ask, well, is this something that we can state in general? This is just an example. The question is how general this observation is. Is it true that a large class of transfer functions exhibits similar behavior? And the answer is yes. And that's the sort of fundamental limit that we are talking about, right? So that's stated in the next slide. So, obviously, observation here is also when zero is negative and small relative to dominant pole at -1, we have large overshoot, right? So all of these sort of relationships between zeros and poles would determine different fundamental limits. And typically, as I said, unstable pole and or unstable zero spell trouble. You may not be able to achieve certain specs. All right, so here is a yep.
So in the previous slide, when you're talking about undershoot when zero is positive, are you getting? Do you think because it's undershoot because zero is positive because of the negative sign?
Undershoot is defined with it's positive even though the response goes down. So the way you define undershoot is the amount. It's like absolute value, how far you go down. So that's why we will talk about positive undershoot, even though the response goes negative before going positive.
You're also saying when C equals to a negative value, you have overshoot and then C is positive drop down. But is that because of the negative sign in the
Negative sign where? It's just an example. I can give you a different example. Don't try to extrapolate this to every system. This is an example. I'm just trying to introduce the issue, and then I want to state a general result in the next slide. So I will give you precise conditions on the transfer functions for which unstable zeros cause problems. So that's the next slide, right? And this is the result. So look, what we're saying that for systems with unstable zero, where C is your zero, right? C is a positive real number, right? And S equals C is 0, right? If I give you, let's say, certain settling time, and I know that I have certain zero, right, that is unstable, then the amount and the undershoot would be lower bounded by this number. So note, the smaller the settling time and the smaller the C, the larger the undershoot would be. So in other words, you will have, responses that look like this, right? You go much further down before you go up, right? That's what would happen. But here's the precise statement of the result. So you can state this result for a much larger class of transfer functions than the example I gave you. So what are the conditions on the transfer functions? Well, we are supposing that G of S is a stable transfer function, so all poles are with strictly negative real parts. We also assume that the G at 0 is 1. This is just an assumption. This formula would be only valid under these assumptions. And also that G at C is 0. Now, what does this mean, G at C is 0? Well, C is the zero of the system. Why do we call, 0 zeros? When we evaluate transfer function at 0, we get that value of transfer function is equal to 0. So this is basically saying that C is a 0 of your system. So, and we assume that C is real valued and positive. This now means that 0 is unstable. So it's a real unstable 0 that we are dealing with. And moreover, we assume that step response satisfies this. Note that we are saying that Y will be within this region for all greater than Ts. So, and delta is roughly 1% of Y infinity. Now, this basically is a definition of settling time. This is a definition of settling time. So the meaning of Ts, that's the settling time for this system. So then the statement that you can have in general under these conditions, right, is that the step response will always exhibit undershoot at the level of this. So undershoot is lower bounded, meaning that you have to go far, by this amount before you start converging to Y infinity, right? So note that this thing here depends on the unstable 0C and settling time. And by the way, approximately for small c and Ts, this whole thing can be approximated. If you develop exponential and Taylor series, neglect higher order terms, you can say, well, approximately this is true for small c times Ts. Yeah. This is where the first sort of inequality comes from. But this bound here is more precise bound than what we have on the top. So first I want you to digest this result. So C comes from the transfer function, right? Settling time is something that your boss may tell you, well, you have to achieve this settling time. So your transfer function was already designed to achieve this settling time. And then boss tells you also, you have to achieve undershoot, equal, 0. But you can't, because undershoot is lower bounded by something positive. For small CTS, this thing here is a positive number. So if your boss tells you have to achieve 0 undershoot and this settling time and blah, 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 you just plug it into this formula and say, well, actually, sorry, it's impossible what you're asking me to do. And then you can start negotiating, okay, that's impossible, but what is acceptable? This is engineering, so it's not mathematics. We can say, well, right, if I can't achieve this, well, if what I can achieve, is that enough? Is that enough, right? So you can start having these sort of conversations. So this tells you basically fundamental constraint on the relationship between unstable 0C, settling time Ts, and undershoot. So there are certain combinations of undershoot, settling time, and unstable zeros that are unachievable by any controller, right? Are there any questions? All right. There are books. So one of the recommended books for you guys is Graham Goodwin's book. Graham Goodwin wrote with two other people, actually my friends, Julio Braslavsky and Maria Serron. They wrote a book on fundamental limits to performance in signal processing and control. So state estimation and control. And that book is full of inequalities like this, right? These inequalities basically tell you what's impossible, right? And it's very useful to know that such book exists, right? Look, I normally don't like going through formulas, in step by step, but I would like to go through this one, the proof, in more detail, because it's insightful. So how you can prove this? You can first define this variable v, which is 1 minus y. 1 minus y. By the way, maximum over this v, or overall time, is actually 1 plus mu, where mu is the undershoot. If you look at, because y is with the minus sign, that's why we have here 1 plus mu. Now, we also know that V is smaller than delta for all t greater than Ts. That's the definition of settling time, right? So V smaller than delta would occur for all t greater than Ts because Ts is the settling time. So by the way, this V is the error between the desired value, which is 1, because we are looking at step response. Desired value, unit step response. Desired value is 1, and then we are looking at the difference between desired response and the true response, y. So if we introduce now Laplace transform of that signal, you can see that, well, the 1 has as Laplace transform 1 over s, because it's the Laplace transform of a step signal. And y is step response. So this is g of s times 1 of s. That's why you get this, right? Moreover, when I evaluate v at c, well, this guy, g at c is 0, because c is a 0 of the system. So what I get is just 1 over c, right? Well, by the way, we can now use the we can just plug, this is the definition of Laplace transform. That's how we define Laplace transform. But I substituted instead of SC, right? I can do that, right? Because this transform is defined for any value of S, right, in the region of convergence. And in this case, because the system is stable, region of convergence is, real part of S is positive. In this case, C is positive, unstable 0. So we are in the region of convergence. So we are good. We can write this. So now you're saying, well, 1 over C is equal. I can divide this integral into part between 0 and Ts and part from Ts to infinity. The integrand stays the same. I didn't change anything here, but I still keep this C there. Now, this part here, you can, say, well, the maximum of this V can be, defined by 1 plus mu. That's the first line up there. So this V, I'm sort of now upper bound with 1 plus mu, and then I keep the integral as before, and then I have here V after time Ts is smaller than delta. So I can upper bound V by delta for all time after Ts. And then you just integrate everything. You get this formula. With a bit of algebraic manipulation, you would get exactly this formula here. It's a rather sort of neat sort of proof, not too difficult to follow, but you can see that, these fundamental limits are there, right? And you can prove that they are there. All right. Another fundamental limit that I want to present, and that's the last result we will present in the lecture, is the following. So if we have slow, what I mean by slow, I mean close to imaginary axis, right? Slow means close to imaginary axis. Slow stable 0, so now I'm talking about stable 0, not unstable 0. And I have small settling time, then you can show that this will constrain overshoot to be sufficiently large. So this is a totally different fundamental limit. Note, the situation is totally different from before, right? We're talking about stable slow 0. We are talking about small settling time. And then we are talking about overshoot rather than undershoot. So here are precise conditions under which this result holds. So suppose GS is a stable transfer function. Again, G at 0 is 1, and G at C is 0. So meaning that C is a 0 of the transfer function. So for real valued, C is now negative. Note, C is smaller than 0. So this is a stable 0. And suppose that we have a dominant pole having real part minus P. So this is a stable transfer function, so real parts are all with negative, right? So P is the closest, corresponds to the pole closest to the imaginary axis. And then we assume that C over P, absolute value, is much smaller than 1. Right? So note that now both 0 and pole are in the left half plane. Both of them are stable. And we are just talking about the case when 0 is much closer to the imaginary axis than the pole. This is what it means. This 2 inequalities, 1 means much smaller than 1. So that means that C is much closer to the imaginary axis. So, and suppose that we consider that unit step y of t that satisfies this. So again, this is the error between y, the true response and the desired response, because the y is the unit step response, right? And we assume that something like this holds for all t greater than ts for some k, and where ts is the settling time for a suitable delta. Then step response has a percentage overshoot bounded, lower bounded by this formula. How to derive this formula? You can follow similar steps as before. It's a bit more involved. I'm not presenting the proof. But what's important is if I tell you I want MP to be, let's say, less than 10%, in this case I can adjust all of these guys so that this is actually larger than 0.1. So it's unachievable. So depending on how you pick now C, TS, K, eta, etc., that would lower bound the overshoot. So again, this is a fundamental limit to performance. Okay. Now, you don't need to learn by heart, all the conditions, but you will. This is an open book exam. So sometimes I might give you a question, and I ask you, please design a controller to achieve this overshoot, but the problem is set up so that you have an stable zero, stable pole, and I gave you an impossible task. So you start designing your controller, but you didn't check whether it's possible to design such a controller. And then people spend 2 hours, I'm not kidding, 2 hours trying to design a controller, but it's just they didn't follow the instructions that I give in lectures, right? So if you have zeros, check these things before you start designing a controller, right? If you have zeros, unstable poles. I mean, I didn't present effects of unstable poles, but you have similar fundamental limits in case of unstable poles as well, right? Okay, so so the first part of this lecture was all about translating desired features of step response to desired locations of poles of the closed loop transfer function. So we learned how to do that. So that's a very important first step in design. And then we also saw that some time domain specifications are unachievable with any linear controller. And in some of them are unachievable with any controller. I'm not going into these details, but I recommended that book by Goodwin, Serron, and Breslavsky, which contains really much more elaborate analysis of these issues. All right. Are there any questions? All right. Well, thank you for your attention. Thanks for being attentive. I am not 100%, so I appreciate it, really. So no consultations this afternoon. Sorry about that. I just can't do it. This is the functional relationship. You look at function, I'm saying with this function that will depend on. So I'm saying this is the value of damping as a functional relationship using that function.
就是它是它不是上面